The night sky is restless again. Across observatories from Arizona to the Atacama, data streams flicker, recalibrate, and whisper of something crossing the dark between worlds. A faint, silvery trace, fainter than a dying comet's breath, streaks across the Martian atmosphere, caught by the Perseverance rover's wide-angle lens. On Earth, monitors flash amber. Algorithms trip over themselves, sorting noise from pattern, signal from myth. For a brief moment, time seems to compress into a single pulse of light. In the silence of command rooms and the hum of global monitoring networks, the name begins to circulate. 3I Atlas, a visitor not born of this solar system, a traveler whose path bends through uncertainty and rumor alike. Analysts argue, NASA insists there is no threat to Earth, and yet defense grids worldwide quietly escalate their readiness. Astrophysicists talk of gravitational assists and orbital resonance, while military satellites reposition in patterns too deliberate to ignore. Somewhere in this delicate web of observation, a paradox begins to form. If there is no danger, why does the world hold its breath? Tonight, we embark on a new journey, where the theme of New 3I Atlas Force's global military alert appears not only as a scientific phenomenon, but also as a question that challenges our imagination. If you enjoy this kind of quiet, long-form storytelling, if it helps you learn, focus, or simply relax at the end of a noisy day, take a moment to like the video and subscribe, but only if this space truly brings you peace. Where are you on the map? Let me know where you are in the world and what time it is in the comments. It's always fascinating to see who's joining us from all around the world. As our story unfolds, we return to the Red Planet on the night of October 3rd, 2025, when Perseverance's camera caught an inexplicable bright streak, the confirmed trajectory of 3I Atlas, glancing past Mars. In the following hours, optical electronic sensors across interplanetary monitoring stations recalibrated, chasing fragments of dust that seem to expand with every observation. At NOIRAB, scientists compared the data to known inner-system comets, only to find discrepancies too precise to dismiss. And then came the transmission, a burst of light, raw and unfiltered, cutting through the Martian night sky, raising a question no one was ready to answer. Was it a military signal, or just an echo of cosmic interference? On the night of the 3rd of October, 2025, in the profound silence of the Jezero crater, the Perseverance rover's unblinking eye chanced upon a singular anomaly, a luminous gash, a diagonal scar of light etched across the Martian firmament. This was not the gentle, familiar gleam of a passing satellite or the diffuse glow of the zodiacal light. It was a sharp, deliberate-seeming streak, captured during a routine calibration sequence of the navcam, a silent event that would soon ignite a firestorm of inquiry back on the distant, blue world. The immediate question, echoing through the halls of the Jet Propulsion Laboratory, was deceptively simple, yet profoundly unsettling. Had humanity just witnessed the first deliberate flash, the first engineered ping from the enigmatic interstellar visitor known as 3I Atlas? Or were we merely confronting a phantom, a trick of the lens and the long exposure in the alien cold? The initial explanation, the one that comforts the rational mind, points to the intricate mechanics of robotic exploration. The Mastcam Z and Navcam systems are programmed with meticulous schedules for nocturnal sky observations, primarily for calibration against known stellar backgrounds, and the raw frames released by JPL are accompanied by precise exposure metadata. A slight, unintended movement of the rover's mast, a shift in orientation during the long accumulation of photons, could readily paint such a streak across the sensor, a digital ghost born of metal and code. This is the narrative of the laboratory, where every anomaly is a puzzle to be solved with data and diagnostics, where the laws of physics as we understand them remain inviolate and sufficient. Yet, Does the sheer, stark geometry of this luminous line, its precise and angular traversal of the sky, fully acquiesce to such a mundane and terrestrial explanation? Should the artifact of instrumentation be conclusively ruled out, the scientific mind naturally turns to the rich and dynamic plasma environment of the Martian system. The tenuous atmosphere, constantly buffeted by the solar wind, is a canvas for electrostatic phenomena. Fine dust particles, levitated by complex charge interactions, could theoretically form transient, ionized structures that discharge and glow. One could hypothesize an unprecedented interaction between this ambient dust and the unique cometary debris field associated with 3I Atlas, a natural, if rare, plasma column ignited by the visitor's passage. Observatories like Noilab possess extensive archives of cometary tail morphologies, and such data could be cross-referenced to seek a match, while updated models of solar wind interaction with Martian atmospheric dust could be run to test the plausibility of such a brilliant, localized emission. But would a naturally occurring plasma event exhibit the spectral purity and the temporal consistency that preliminary analysis might yet reveal hidden within the pixel data? This leads us to the third and most profound tier of speculation: the possibility that the streak was neither accident nor natural wonder, but a signal, a structured, periodic beacon. The very designation, 3I, marks its origin as outside our solar system, a traveler from the galactic void, and its trajectory, a hyperbola, speaks of a journey of immense duration and distance. If this light was a message, a targeted transmission, it would imply a technology capable of focused radiative targeting across light years, a civilization not only present but attempting to make its presence known. The established protocols would snap into action. The SETI Institute's pipelines for narrowband signal detection would be tasked with reanalyzing all ground-based radio telescope data from that moment. Military and intelligence channels might request priority access to global antenna arrays, seeking confirmation, a silent, non-responsive contact protocol, long drafted for such an eventuality, would be cautiously activated. The opportunity would be unparalleled, a chance to locate and perhaps even decipher an interstellar technology. But does the immense promise of such a discovery not carry with it a corresponding and grave risk? The risk of triggering a global security and information confrontation that could overshadow the scientific wonder itself. The confirmation of an interstellar origin for the object, now being meticulously tracked by a synchronized network of deep space telemetry, has irrevocably shifted the context of every observation. It is no longer merely a celestial body, it is an envoy. The precise hyperbolic arc of its journey, calculated and confirmed by the IAU's Minor Planet Center and NASA's PDCO, tells us it is not from here, that it has sailed the great ocean between the stars. This fundamental fact now casts the strange light over Jezero in a new and infinitely more consequential light. If it was a signal, then who was it for? Was it a general broadcast into the darkness, or was it, as the timing and the location might suggest, a specific greeting aimed at the one technological outpost we have placed on another world? The very synchrony required for such targeting would suggest a knowledge of our activities that is both deeply observant and unsettlingly precise. And so, we are left at a precipice, staring into a darkness that has suddenly become aware. The red alert is not merely about a streak of light on a photograph, it is about the past, fragility of our understanding, and the monumental weight of a single, simple question. The laboratories will continue their work, the spectrographs will dissect the light, and the simulations will run, but a threshold has been crossed. The serene, objective pursuit of science now brushes against something far more momentous, something that demands a response not just from our instruments, but from our very civilization. For if the light was a call, then what manner of voice will we use to answer? The protocols are in place, the networks are synchronized, tracking the hyperbolic path, But are we, as a species, truly prepared for the next step? For the moment when a simple streak of light demands, we define our place in a cosmos that is no longer silent. The instructions have been issued. The global network of eyes is now fixed upon the hyperbolic trajectory, a path that confirms a truth, both exhilarating and terrifying. We are not alone. And with that confirmation, a new directive echoes across the listening posts of Earth, a command that transforms observation into a state of heightened vigilance. The silent sentinels of our planet, a synchronized network of telescopes spanning from the high deserts of Chile to the volcanic peaks of Hawaii, have traced a line against the celestial sphere that does not lie. Their collective gaze, calibrated to the minute tremors of starlight, has converged upon an object whose trajectory is an affront to the gravitational dominion of our Sunday. The Minor Planet Center has published the orbital elements, and the numbers speak a stark and simple truth: an eccentricity greater than 1. This is not a member of our solar family, bound in an eternal dance around its central fire. This is a visitor from the abyss, a solitary voyager on a hyperbolic path that will enter our realm only to depart forever. Its designation, 3I Atlas, marks it as only the third confirmed interstellar interloper in all our recorded history. But its path is the most unequivocal. The sophisticated astrometry, processed by the European Space Agency and NASA, drawing from the panoramic surveys of pan-stars and the asteroid terrestrial impact last alert system, leaves no room for doubt. The very precision of these measurements, the remarkably low astrometric residuals across a global chain of observatories, confirms the trajectory with a certainty that is both a triumph of computational astronomy and a profound philosophical challenge. What does it mean when the sky, once a map of familiar constants, delivers a trajectory that belongs to another star? Confronted with this celestial anomaly, the scientific mind instinctively seeks to categorize, to explain, within the comforting confines of known phenomena. The initial, most conservative hypothesis posits that we are witnessing a primordial relic, an ancient comet of ice and dust from the deep freeze of interstellar space, now being warmed for the first time in billions of years by our sun's faint breath. As it approaches the inner solar system, the theory goes, solar radiation will begin to vaporize its volatile ices, potentially revealing a coma and a tail, allowing instruments like the Hubble Space Telescope and the Keck Observatory to capture its reflection spectrum. The presence of specific absorption lines, signatures of water ice, complex organic molecules like tholins or silicate dust would provide a natural, albeit extraordinary, explanation for its origin. This would be a gift from the galactic library, a pristine sample of the building blocks that form around other stars, and its study would update our statistical models for the density of such nomadic objects drifting through the galactic plane. Yet, the very inertness of such an object, its predictable and mindless journey, raises a question that the spectrum alone cannot answer. In a galaxy as ancient as ours, is it not statistically inevitable that some of the debris cast out from other planetary systems would bear the imprint, not of nature, but of intelligence? This line of inquiry leads to a second, more speculative tier of hypothesis that 3I Atlas is not a simple rock, but an artifact, a piece of ancient technology, a derelict from a civilization that rose and fell long before Earth had even cooled, now wandering the void as a silent tombstone. It would be a profoundly tragic object, a message in a bottle with no intended recipient, its creators long since turned to dust. The Doppler radar systems of the Deep Space Network and the Goldstone Observatory stand ready, their powerful transmitters capable of pinging the object if its size and distance permit, listening for a radar echo that might reveal an unnaturally smooth surface or a complex geometric shape. A lack of any such anomalous structure, a confirmation of its inert and non-responsive nature, would still ignite a firestorm of debate about its technical origins, a debate forever unresolved. But what if the echo that returns is not merely a reflection, but a modulation? This precipitates the third and most consequential level of consideration, the possibility that the object is not a derelict, but an active device. Such a hypothesis immediately bifurcates our future, forcing a schism between the open inquiry of civilian science and the controlled protocols of planetary security. The very institutions that collaborated to discover the object would find their data streams partitioned, their access tiered. A silent, global, listen-only radio fence would be erected, a directive to observe but not to provoke, to learn but not to engage. The opportunity to construct a map of interstellar traffic flow, to lay the groundwork for an entirely new field of cosmic security, would be weighed against the immense risk of a fractured and competitive race to claim the right to query and to define this enigmatic target. Does the act of reaching out to an unknown intelligence represent humanity's greatest aspiration or its most profound folly? This is the paradox of the alert. While NASA and other scientific bodies publicly declare that the object's trajectory poses no threat to Earth, a necessary statement of factual orbital mechanics, the strategic defense centers of the world have quietly elevated their readiness levels. The public hears a message of calm assurance, while within secure facilities, the screens glow with tracking data and contingency plans are pulled from their vaults. The dissonance is not born of deception, but of the fundamental uncertainty of the object's nature. One can be certain of its path, yet completely in the dark about its purpose. The declaration of safety pertains only to its gravitational influence. It says nothing of its intent, should it possess any. How does a civilization prepare for a first encounter that is simultaneously a scientific bonanza and a potential paradigm shift of unknowable scope? In the silent, airless expanse beyond our world, where celestial mechanics dictates the motions of worlds with an unerring and predictable rhythm, the announcement from the Planetary Defense Coordination Office arrives with the cool, measured cadence of pure science. The object, a visitor from the interstellar deep, poses no threat of kinetic impact. Its trajectory, plotted against the star fields by the vigilant eyes of the James Webb Space Telescope and a global network of radio observatories, will pass at a safe and calculable distance. According to current models of orbital dynamics, the laws of physics, as articulated by Newton and refined by Einstein, assure us that this particular cosmic wanderer will not scar the face of our planet. Yet, beneath this placid surface of scientific certainty, a different kind of calculus is being performed in the windowless rooms of National Space Operations centers, where the steady-state readiness levels are quietly, almost imperceptibly, being elevated. If the risk is not one of collision, then what unseen force compels this heightened state of vigilance, this subtle mobilization of assets designed for scenarios far removed from peaceful astronomical observation? The paradox is not one of mass and velocity, but of perception and information. The official narrative, meticulously crafted and publicly disseminated, correctly addresses the primary concern of planetary safety, utilizing established scales like Torino and Palermo to quantify the infinitesimal probability of a physical impact. These scales are the lexicon of astronomers, a language of risk assessment that speaks to the raw, physical power of celestial bodies. Simultaneously, however, a separate and distinct lexicon is invoked within strategic command centers, one that speaks not of impact probabilities, but of informational threats and geopolitical instability. The true risk, therefore, may not reside in the object's trajectory, but in the shadow it casts upon the global psyche, a shadow that could be manipulated, distorted, or weaponized in the theater of international relations. Could it be that the object itself is merely a catalyst, a neutral piece of cosmic debris around which a storm of human uncertainty is destined to form, regardless of its benign physical nature? This divergence in response protocols reveals a fundamental schism in how humanity perceives threats from the cosmos. The scientific community, embodied by institutions like NASA, operates on a principle of transparent observation, its mission to understand and to inform. The defense and intelligence apparatus, however, is bound by a doctrine of strategic ambiguity and preparedness for the unknown. The historical precedent of the first interstellar objects, one named Oumuamua and the other Borisov, serves as a poignant case study. While public scientific discourse focused on their composition and origin, a parallel and less visible process of military and intelligence monitoring was undoubtedly underway, assessing these enigmatic travelers not as subjects of study, but as potential vectors of disruption. The public message was one of cooling temperatures, while the secure channels maintained a steady watch. Is our civilization therefore developing a split personality in its approach to the cosmos? One face open and inquisitive, the other guarded and perpetually wary? The escalation of readiness within these watch centers unfolds not as a single alarm, but as a symphony of graduated protocols, each movement more restrained and clandestine than the last. The first level is one of heightened awareness and narrative control, a deliberate effort to monitor and counter the unpredictable ecology of rumors and misinformation that flourishes in the digital age. The second level engages a more technical surveillance, deploying multispectral signal analysis and tightening access to sensitive data streams, effectively creating a cordon sanitaire around the information pertaining to the object. But it is the third and most profound level that truly hints at the depth of the concern, a protocol that mandates radio silence from our most powerful transmitters, a deliberate muting of our technological voice to prevent our world from broadcasting its unique electronic signature into the void. What does it signify when our most prudent course of action is to hide from the universe, to pretend we are not here? This intricate dance between public assurance and private contingency relies on a fragile mechanism, often described as two channels. One voice, where scientific clarity and security necessity strive to present a coherent, if not entirely transparent, front to the world. The scientists speak plainly of orbital mechanics, while the security officials speak sparingly, yet in a manner consistent with the overarching narrative of control. The greatest vulnerability in this carefully constructed system is not a failure of technology or a miscalculation of an orbit, but a collapse of public trust. Should the dissonance between the two messages become too apparent, revealing the profound anxiety that lurks beneath the calm exterior of official statements? Can a civilization maintain its composure when it realizes that its guardians are preparing for threats that its scholars cannot even name? And as this silent watch continues, a new data point emerges, not from the void of interstellar space, but from within our own solar system, a signal that serves as the ultimate input for our planetary defense protocols. The silent, rust-colored sphere of Mars, hanging in the blackness, has for centuries been a subject of human fascination, a world upon which we have projected our hopes for life and our fears of solitude. Yet, this passive neighbor in the solar system may hold a role far more profound than that of a mere geological specimen, as suggested by a sequence of events initiated by a simple, routine maneuver, a spacecraft flyby. When a human-made object swings past the red planet, using its gravity to adjust its trajectory towards some deeper destination, it does not pass unnoticed. Across hundreds of millions of kilometers, a silent alarm is tripped. Deep space network antennas, their colossal dishes tuned to the faint whispers of the cosmos, subtly shift their scheduled operations, their calendars reprioritized in an instant. Orbiters like the Mars Reconnaissance Orbiter and MAVEN, already diligently mapping canyons and sampling the thin atmosphere, begin listening not to the planet below, but to the space around it. Their instruments are tuned to the faintest perturbations in the local plasma. This is not a response to a known signal, but to an event, a ripple in the quiet pond of interplanetary space. Could it be that the mere passage of a small inert object serves as a key, unlocking a pre-programmed sequence of planetary-scale observation, a protocol written not by human hands, but by the implicit logic of a system we do not yet comprehend. From the perspective of conventional science, this coordinated response is a masterpiece of modern engineering, a testament to our growing capabilities in planetary defense and situational awareness. The activation of wide-field survey telescopes, such as Atlas and the Zwicky Transient Facility, shifting into a higher cadence of observation, is a prudent measure to rule out any associated debris or unforeseen cometary activity in the vicinity. The real-time assessment of the object's trajectory by automated pipelines like Scout at the Jet Propulsion Laboratory is a standard procedure for calculating impact risks and orbital dynamics. This entire ballet of data collection and analysis can be understood as a sophisticated drill, an invaluable opportunity to test our planetary defense infrastructure in a real-world, though controlled, scenario. The resources dedicated, the precious observation time on premier telescopes, the computational power, the focus of orbiting assets are a calculated expenditure, a necessary investment in safeguarding our own world against future, genuinely threatening encounters. Yet, one must ponder, is the sheer scale and immediacy of this response entirely commensurate with the known stimulus, or does it hint at a deeper, more unsettling hypothesis we are reluctant to voice aloud? The first and perhaps most intriguing hypothesis posits that the flyby is not merely a gravitational assist, but a functional act, a ping in a vast interstellar geodetic system. Much like a ship using sonar to map the ocean floor, our spacecraft, by its very presence and velocity, might be providing a datum point for a network whose existence we can only infer from its reaction. The precise trajectory and mass of the flyby object create a minuscule but calculable distortion in space-time, a ripple that could, in theory, be detected by a system sensitive enough to monitor the gravitational fabric of the solar system. This would imply a level of engineering so advanced that its operational principles border on the imperceptible, a system for which our most complex machines are but transient blips on a cosmic radar. The coordinated shift of sensors across multiple wavelengths, optical, radio, infrared, suggests an attempt to gather a complete signature, to understand not just the object, but the nature of the ping itself. If this is a test, are we the ones administering it, or are we, and our spacecraft, merely the subjects of an examination whose purpose remains entirely opaque? A second, more conventional explanation lies in the complex interplay of celestial mechanics and Martian geology. The gravitational tug of a passing object, however small, combined with the relentless pull of the solar tide upon Mars, could theoretically act as a trigger for a transient outgassing event. The hypothesis suggests that tidal forces could open subsurface faults, releasing trapped reservoirs of carbon dioxide or water vapor in a brief, shimmering plume, a phenomenon that orbiters like MAVEN are exquisitely designed to detect through changes in atmospheric composition and local plasma disturbances. This would frame the entire monitoring sequence as an attempt to capture a rare and fleeting geological process, a chance to witness the Martian interior breathing, however faintly. But that does not account for the specific timing, the precise alignment of the monitoring protocol with the moment of closest approach, as if the system were anticipating a reaction rather than observing a random occurrence. Could a natural tidal-induced venting explain the urgency, or are we observing an effect being mistaken for a cause, a symptom of a much more deliberate process? The most speculative, and therefore most profound, hypothesis ventures into the realm of the truly alien. It proposes that our solar system is not empty, but seeded with dormant technology, ancient probes, perhaps millions of years old, resting in the deep freeze of space or on the surfaces of barren worlds. The flyby, according to this line of thought, does not merely pass by Mars. It enters a different magnetic environment, a distinct region of the heliosphere. This transition could act as an environmental key, a change in the local weather that signals a wake-up call to a sleeping sentinel. The subsequent global surveillance would then be the probe's initial systems check, its sensor suite coming online to assess the new object in its vicinity, an object possessing a hyperbolic velocity that marks it as an outsider. This would transform our understanding of the solar system from a collection of inert rocks to a landscape that may be actively managed, or at least passively monitored, by intelligences beyond our own. The very laws of physics, which we believe to be universal constants, might in this context be merely the local bylaws of a territory we do not control, and the silent wakefulness of these hypothetical sentinels forces us to confront a terrifying possibility. Have we been living in a garden we mistakenly believed was a wilderness? The response itself escalates through distinct tiers of engagement, a structured protocol that unfolds with a chilling automated logic. The first level is one of pure optical tracking, a simple act of marking the object's position against the starfield, a basic confirmation of its existence and trajectory. But this is swiftly superseded. The second tier integrates the full spectrum of sensing radio telescopes, listening for non-natural emissions, infrared instruments seeking the heat signature of propulsion, ultraviolet sensors, analyzing the composition of any potential coma or plume. Concurrently, sophisticated computer models begin to simulate the object's passage, calculating the expected interactions with the solar wind and the Martian exosphere, creating a dynamic model of its wake. This is no longer simple observation, it is an intensive effort at characterization, as if attempting to build a complete profile of the visitor. What could necessitate such a comprehensive and immediate background check on a piece of human technology whose blueprints we already possess? It is the third and final level of response, however, that most clearly diverges from standard scientific practice and veers into the territory of strategic defense. This involves the establishment of a non-emitting surveillance box, a volume of space monitored by passive sensors only. Within this box, powerful simulations are run, not of the object's current path, but of hypothetical future trajectories, potential rendezvous points, gravitational keyholes that could alter its course toward Earth or other sensitive locations within the inner solar system. This is the moment the exercise transcends geology and astronomy and becomes an act of celestial wargaming. The expenditure of resources is no longer merely about scientific curiosity. It is a strategic drain, pulling focus and capability from other missions, other discoveries, in the name of planetary security. This raises an unsettling pragmatic question. Are we, in our vigilance, inadvertently training our systems to recognize a threat that does not yet exist? Or are we, for the first time, beginning to perceive the faint outlines of a battlefield that has been in place for eons? The flyby, therefore, stands as a paradox. It is a controlled experiment, a natural test of our planetary defense readiness that provides invaluable data on our own capabilities and response times. Yet, it is also a potential trigger, an event that seems to elicit a response from a system whose parameters we are only beginning to map. The very act of observing the observer creates a feedback loop of profound metaphysical implications. We use the flyby to test our sensors, but the coordinated activation of those same sensors may be the primary data point in a larger, unseen experiment. The risk is not merely the consumption of telescope time or computational cycles, it is the potential for a fundamental reordering of our place in the cosmos, a shift from being the sole subjects of our own story to becoming characters in a narrative whose plot we cannot discern. And as the silent, automated protocols complete their cycles and the data streams back to Earth, one is left to wonder if the most significant outcome of this entire exercise is not the data we have collected, but the simple, terrifying fact that we felt the need to collect it in such a coordinated and urgent fashion. For in the silent wake of the passing spacecraft, as our global network of eyes and ears turns its attention to a single point in the void, we are left to contemplate the nature of the threshold we may have just crossed. A threshold defined not by distance, but by awareness itself. But what if this event is merely the first, faint echo of a much larger pattern, a single data point in a map we have not yet learned to read? The true significance of the flyby may not lie in the momentary flurry of activity it inspires, but in the cold, hard numbers that define its journey, its speed, and its direction, the very vectors that portray its origin. For the object's hyperbolic excess velocity and its approach vector are the ultimate clues, the cosmic fingerprints that speak of distant stars and the vast, uncharted pathways between them. In the profound and silent darkness between the stars, every visitor carries with it a map of its journey, a story written in the language of motion. The hyperbolic excess velocity and the approach vector of an interstellar object are more than mere astronomical data points. They are the opening lines of a cosmic narrative, a trajectory that traces back to an origin shrouded in the impenetrable depths of time and space. When an object like the one designated 3I Atlas was first observed, its path was not a gentle curve bound by the sun's gravity, but a stark, decisive line cutting through the ecliptic plane, a vector that spoke of a journey beginning far beyond our local stellar neighborhood. This vector is the fundamental clue, the first and most critical piece of evidence in a detective story that spans light years. It is the initial brushstroke on a canvas that depicts not just our solar system, but our galactic vicinity, a nascent chart of what could be called interstellar geography. The velocity, a residual signature remaining after the sun's gravitational pull is accounted for, tells of forces that acted upon it long before it entered our sphere of observation, whispering of gravitational slingshots, of close encounters with unseen stars, or perhaps of something else entirely. Could it be that by meticulously plotting these trajectories, we are inadvertently drawing the first lines of a map that details not natural phenomena, but structured pathways through the void? According to current models of galactic dynamics, such hyperbolic objects are the inevitable statistical outcome of gravitational perturbations within the galaxy. Stars, like ships passing in the night, exert subtle influences on the vast reservoir of cometary bodies theorized to exist in the Oort cloud of every star, occasionally ejecting one with sufficient velocity to send it on a million-year journey between solar systems. The initial analysis of 3I Atlas's radiant, the point in the sky from which it appeared to originate, suggested a past encounter, a gravitational nudge that could be traced back through the eons. By employing sophisticated orbital mechanics to run its trajectory in reverse, and then cross-referencing this calculated path with the exquisitely precise stellar cartography of the Gaia Data Release 3, astronomers seek the culprit, a faint red dwarf star that passed within a light year or two, its gravity a gentle but decisive hand altering the object's destiny. This is the first and most conservative hypothesis, that 3I Atlas is a solitary wanderer, a piece of natural debris cast adrift by the random and chaotic currents of galactic gravity, its extraordinary velocity merely a testament to the power of a stellar flyby. But does the simple randomness of celestial mechanics fully account for the precise alignment and the specific characteristics of its approach? Or are we witnessing the first faint signature of a more organized stream of interstellar material? The spectroscopic data, when compared to the only other confirmed interstellar visitor, 2I Borisov, reveals a tale of two distinct compositions. While 2I Borisov presented a familiar profile, rich in carbon monoxide and water ice, reminiscent of the comets that dwell in our own outer solar system, 3I Atlas was an enigma, its spectral lines hinting at a mineralogy that is both alien and difficult to place within our current understanding of planetary formation. This compositional dissonance immediately challenges the notion of a uniform galactic population of icy planetesimals. Furthermore, the statistical analysis of its residual velocity, measured against the standard of the local standard of rest, the average motion of stars in our immediate galactic vicinity yielded a value that sits at the extreme edge of probability. It is not merely fast, it is anomalously so, as if it were not just ejected, but propelled. This leads to a second, more speculative hypothesis, that we are not observing random ejecta, but a member of a coordinated stream. Such a stream could be the result of a single, cataclysmic event in a distant system, a planetary collision, a stellar explosion, or the gravitational shredding of a planetesimal disk by a passing star. The objects within this stream would share similar vectors and velocities, creating a kind of interstellar river, a pre-established corridor through which material flows. Is it possible, then, that our solar system is currently intersecting one of these cosmic currents, and that 3I Atlas is but the first recognizable flotsam carried on its tide? Yet, there remains a third, and far more profound, level of interpretation. What if the pattern is not merely a natural river, but something resembling a constructed route? The concept of an interstellar freeway is not one of paved roads, but of optimized trajectories, paths through space that minimize travel time or energy expenditure, using the gravitational wells of stars as natural accelerators. If multiple such hyperbolic objects were to be discovered over the coming years, and if their approach vectors were to cluster around specific radiants, repeating a pattern that cannot be explained by known stellar encounters, the hypothesis would demand a radical escalation. The anomalies would compound, pushing against the very limits of the laws of physics as we understand them. The velocity, the composition, the trajectory, all could be interpreted as components of a system, the faint but detectable signature of a technological infrastructure operating on a galactic scale. The emissary would not be a randomly ejected rock, but a piece of targeted traffic, either a vessel itself or a piece of debris from its wake. This is the ultimate implication of the vector map, that we are not merely mapping natural dynamics, but potentially charting the activity of a civilization whose engineering projects are of such a magnitude that they have become visible across the interstellar distances. Are we, in our cautious scientific analysis, inadvertently decoding the first signs of an organized presence in the galaxy? And if so, what does that say about our own place in the cosmic hierarchy? The opportunity presented by this new field of interstellar geography is unparalleled, a chance to move beyond the parochial confines of our solar system and understand our position within a dynamic and interactive galactic environment. Each new hyperbolic object is a data point, a probe from a distant stellar system that delivers, for free, information about its data origin. By building a census of these visitors, we can begin to understand the frequency of planetary system interactions, the composition of exo-Oort clouds, and the gravitational history of our local cosmic neighborhood. It is a new form of astronomy, one that turns the entire solar system into a sensor array for galactic phenomena. Yet, this grand opportunity is shadowed by a profound risk, the peril of misinterpreting the faint and ambiguous signals from the dark. The human mind is a pattern recognition engine, often seeing intention in coincidence, agency in accident. To overinterpret the data, to leap too quickly to the conclusion of technological origin, could have significant consequences, potentially triggering misguided policy decisions rooted in fear rather than fact. The very use of the term interstellar freeway carries a cultural and psychological weight that could skew the scientific discourse, pushing it toward a security-centric paradigm rather than one of pure exploration. How do we navigate this treacherous strait between the Scylla of myopic skepticism and the Charybdis of premature extrapolation, when the stakes involve our very understanding of life in the universe? The answers, as always, lie in more data, in the next observation, the next visitor, and the next chapter of this story has a date and a location. All speculation, all analysis of its incoming trajectory, will be put to the test as the object reaches its point of closest approach to a neighboring world, a moment that will allow for a crucial calibration of our instruments and our theories. The Martian atmosphere, thin and transparent, provides a pristine backdrop against which to observe the object's behavior, its outgassing, and any persistent dust trail it might leave in its wake. This encounter is not merely a celestial event, it is a diagnostic procedure. The sophisticated electronic optics of our deepest space telescopes and orbiting observatories will be trained on this rendezvous, their sensors pushed to their limits to capture every photon, every subtle change in the object's luminosity and spectrum. The data streamed back will be the ultimate arbiter, confirming or refuting the existence of a discernible coma or tail, features that would firmly place it within the realm of natural cometary bodies, or alternatively, revealing a stark, inert minimalism that would only deepen the mystery. Will this close passage past the red planet illuminate the object's true nature, or will the data it generates only serve to further obscure its origins, forcing us to confront even more fundamental questions about the fabric of reality itself? The 3rd of October, 2025, marks a pivotal moment in this investigation, a date with a Martian encounter and the definitive confirmation of a trailing streak, a critical calibration of our electronic optical sensors. On the 3rd of October, 2025, a routine maneuver at the edge of human perception became an event that would quietly recalibrate our entire watchful network. A spacecraft, one of our silent mechanical envoys, performed its scheduled close approach to the ochre sphere of Mars, its optical sensors trained not upon the planet itself, but upon the void beside it, where an enigmatic streak had been intermittently logged. The initial assumption, a comforting one, was that this was a final, critical moment for sensor calibration, a chance to use a known, if puzzling, a phenomenon to refine the instruments that guard the inner solar system. This close pass, however, transformed from a simple calibration exercise into a moment of profound and unsettling revelation, forcing a collective re-evaluation of the very tools with which we seek to comprehend the cosmos. What began as a technical procedure ended as a philosophical challenge, forcing us to ask if our most trusted eyes were seeing a flaw in the machine or a truth in the void. According to established protocols of observational astronomy, the first and most logical step was to treat the anomaly as a product of instrumental error. Teams across the globe initiated the sacred trinity of photometric correction: the bias frame, which maps the electronic whisper of the sensor itself, the dark frame, which captures the thermal noise born of mere existence in the void, and the flat frame, which corrects for the minute variations in pixel sensitivity and optical vignetting. This rigorous process, the fundamental hygiene of data collection, was applied with unprecedented coordination, cross-referencing data from other Mars orbiters, and even the surface-based cameras of the Perseverance rover. The point spread function, the unique fingerprint of how a telescope distorts a point of light, was meticulously matched across these disparate platforms, a testament to our desire to find a common, mundane origin for the streak. We sought a ghost in our own machines, for a known ghost is a comfort compared to an unknown celestial phenomenon. Yet, the streak persisted. It defied the cleansing rituals of calibration, remaining as a faint but statistically significant imprint on the data. This resilience against our best efforts at eradication opened the door to the first tier of speculative hypotheses. Could this be the signature of an object in an impossibly slow rotation, a cosmic monolith tumbling with a ponderous gravitational grace over centuries? The standard explanation for such linear features in deep space imagery often points to a tumbling asteroid or a discarded booster, their changing albedo creating a dashed line of light. But that conventional model relies on a predictable periodicity, a rhythm that can be extracted from the light curve. The data from this event yielded no such rhythm. The light curve was a flat, enigmatic line, suggesting not a periodic variation in brightness, but a constant, steady emission or reflection. This absence of a pulse, this silent, unwavering signal, was more disquieting than any pattern we could name. This led to a more nuanced technical conjecture, the rolling shutter effect. Modern digital sensors do not capture an image all at once, but scan across the field of view line by line, much like the eye of a reader moving down a page. If an object is moving with a specific velocity relative to the spacecraft, and its brightness is just at the threshold of detection, this sequential scanning could theoretically stretch a point of light into a linear smear, a pillar of data where there should only be a pinprick. Scientists suggested this could be due to a small, high-velocity object passing through the field of view during the exposure, its faint light painted as a line by the sensor's methodical readout. It is an elegant solution, one that neatly confines the mystery within the known laws of optics and engineering, transforming the celestial into the procedural. But what if the object itself was the source of the anomaly? The third, and most profound, hypothesis emerged from the analysis of its spectral signature. When data from the Hubble Space Telescope and several ground-based observatories were collated, the reflected light from the streak revealed a composition that defied easy categorization. It did not match the familiar spectra of water ice, of carbon dioxide, or of silicate rock. The reflection was odd, muted in some common wavelengths yet surprisingly bright in others, suggesting a material with a crystalline structure or elemental purity not commonly found in the random debris of our solar system. This was not merely an object, it was an object made of something other. Could it be that we are not looking at a simple smear of light, but at the glint of a manufactured surface, or a natural material forged in an environment far different from our own? Thus, the investigation unfolded across three distinct tiers of understanding, each layer pulling us deeper into a web of implication. The first level was one of practical resolution, a closed case of sensor calibration that provided a comforting, if temporary, closure. The second tier expanded the scope, forcing a new era of interagency, multi-mission standardization, a global effort to ensure every electronic eye was speaking the same language, a project born from a shared, unspoken anxiety. But it is the third tier that continues to resonate within the halls of observatories and the minds of theorists, the persistent, resilient anomaly. This was not an error to be corrected, but a signal to be understood. Its very endurance necessitated an upgrade to the very algorithms that scan the skies, a silent directive to teach our machines to look not just for known rocks and comets, but for the subtle, telling signatures of the interstellar visitor. For if our sensors can be so easily fooled by a natural phenomenon, how many true visitors have we already missed, their passage recorded only as a glitch to be filtered out and forgotten? This meticulous recalibration, this quiet upgrade of our planetary senses, was not merely about solving a single mystery. It was a necessary preparation, a honing of the blade for a far more significant encounter lurking just weeks in the future. An appointment with an object that would soon reveal its deepest secrets at the point of its closest embrace with our Sunday. The stage for that next act was set at a distance of 1.4 astronomical units, a specific point in the grand elliptical clockwork of the solar system, known as the perihelion. On the 30th of October, 2025, this object, now the subject of such intense and quiet scrutiny, would reach its closest approach to the ferocious nuclear heart of our star. This moment, this perihelion passage, is for a celestial body, a trial by fire, a transformative event where hidden ices are awakened into brilliant, sunlit comas, and the very structure of the object is tested by solar radiation. It is here, in that blistering proximity, that the true nature of the object would be laid bare, not as a mere streak of light or a sensor ghost, but as a physical entity with composition and form. The cryptic streak observed near Mars was but a prelude, a faint signature in the dark. The perihelion would be its grand, illuminated performance. At this pivotal moment, Our newly refined and globally synchronized network of telescopes would turn its collective gaze, not to look for a flaw, but to measure a reality. The primary objective would be to dissect the composition of any resulting coma or tail, to use spectrographs to read the chemical poetry written in the light of vaporizing gases. The presence of water, of carbon monoxide, of cyanogen, or other volatile compounds would instantly classify the object within the known families of our solar system, taming the anomaly with the power of nomenclature. The very morphology of the tail, whether it is short and stubby, indicating larger dust grains and stronger internal cohesion, or long and wispy, suggesting a fragile aggregate of ice and dust, would speak volumes about its history and its origin. We would be conducting a celestial autopsy on a living object, learning its secrets as it is transformed by stellar fire. Yet, the hypotheses prepared for this event reach beyond the conventional. What if the spectral analysis reveals not the common cometary volatiles, but simpler, more refractory materials, or complex carbon chains that speak of a genesis in the cold, dark molecular clouds of interstellar space? The mainstream explanation would point to a unique mineralogical composition, a rock forged in a peculiar planetary system since gone. But that would not account for the peculiar, non-gravitational accelerations that such an object might exhibit, tiny deviations in its trajectory that the laws of Kepler and Newton cannot explain. Such deviations could be caused by the gentle, rocket-like thrust of outgassing, a natural process. However, if the outgassing is absent or does not align correctly to produce the observed trajectory, one is left with a far more provocative possibility. Could the morphology of the tail, its structure and dynamics, reveal not just the action of solar radiation pressure, but something else? Something like a form of photon sailing or a subtle manipulation of its own trajectory. The data collected at perihelion would be irreplaceable, a one-time opportunity to observe the object in its most active state. The light curves would be at their most dynamic, the spectroscopic signals at their strongest. Every major observatory, from the Atacama Desert to the peaks of Hawaii, and every space-based asset, from the aging but formidable Hubble to the powerful new James Webb Space Telescope, would have their instruments locked onto this single point of light. The very coordination forged in the aftermath of the Martian anomaly would be put to its ultimate test, creating a symphony of observation across the electromagnetic spectrum. This was no longer about calibrating sensors. It was about calibrating our understanding of what is possible within the boundaries of our solar system and what might have arrived from beyond. The long-term implications are profound. A confirmed interstellar object, especially one exhibiting unusual properties, represents more than a scientific curiosity. It is a physical sample from another star system, a messenger bearing information about the formation of other worlds. The detection and detailed study of such an object is a cornerstone of the burgeoning era of the four eyes, interstellar inquiry, a paradigm shift towards the systematic search for and analysis of visitors from other solar systems. The efforts to reduce long-term false alarms, initiated after the October 3rd event, find their ultimate justification here, in the clean, unambiguous collection of data from a true interstellar interloper. By minimizing the noise of our own technology, we sharpen our ability to hear the faint signal of the other. But as we prepare to witness this celestial object at its moment of stellar intimacy, to dissect the composition and morphology of its dusty tail, we must confront the most unsettling and captivating question of all. What if the tail is not a tail at all? What if, under the most intense scrutiny, the cloud of dust and gas surrounding the object resolves not into the chaotic, beautiful plume of a natural comet, but into something with a pattern, a structure, or a symmetry that speaks not of random sublimation, but of directed purpose? The possibility remains, hanging in the void like the object itself, that we are not just observing a rock, but an artifact, and that the light we see is not merely reflected, but perhaps even transmitted. The void between worlds is not truly empty, for it is a canvas upon which the comets paint their transient signatures, brief and brilliant calls against the silence. As this traveller approaches its perihelion on the 30th of October, 2025, at a distance of 1.4 astronomical units from our star, it offers a singular moment of revelation, a fleeting window into its most intimate nature. This is the moment when the object, warmed by the solar embrace, begins to speak, to tell its story through the material it sheds. According to current models, this activation is a predictable, if dramatic, phase in the life of a comet, where volatile ices locked within its nucleus for eons finally succumb to the heat, sublimating directly into gas and dragging with them a cloud of fine dust to form the iconic coma and the sweeping tails that have captivated humanity for millennia. Scientists suggest this could be due to the progressive heating of a surface rich in water ice, carbon monoxide, and other frozen gases, a process we have observed countless times in both short-period comets and visitors from the distant Oort cloud. The initial hypothesis, therefore, is one of a natural outburst, a cosmic exhalation where previously hidden, volatile materials are exposed to the vacuum of space, creating a temporary, vibrant atmosphere around the wandering nucleus. Yet, as we prepare our greatest eyes on the sky, the Keck Observatory, the Very Large Telescope, the enduring Hubble Space Telescope to capture the spectrum of this event, we must ask if this simple narrative of evaporation is sufficient to describe what we might witness. Could the act of a comet introducing itself hold nuances we have never before been capable of perceiving, or perhaps never had the reason to look for? The initial data will arrive as light, fractured into its constituent colors and translated into the language of chemistry by our instruments. The emission spectra, the bright lines betraying the presence of cyanogen, diatomic carbon, amidogen, and water vapor, will be scrutinized with unprecedented precision. This is the standard lexicon of cometary composition, a familiar alphabet of cosmic chemistry that speaks of molecular clouds and the primordial conditions of our solar system's birth. The narrowband images, focused on the forbidden green line of oxygen and the yellow sodium doublet, will map the structure and velocity of the gas, revealing the dynamics of the coma as it is shaped by the photon pressure of sunlight itself. Concurrently, data from the MAVEN orbiter at Mars and the venerable Solar and Heliospheric Observatory will provide a real-time map of the solar wind, allowing us to disentangle the ion tail's morphology from the complex interplay of the comet's own emissions and the relentless stream of charged particles flowing from the sunday. The mainstream scientific explanation posits that the shape and behavior of these two tails, the broad, curving dust tail and the straight, sharply defined ion tail, are a direct consequence of well-understood physics, with the dust pushed by radiation, pressure, and the ions tracing the magnetic field lines embedded in the solar wind. But what if the morphology we observe defies this clean separation? What if the dust and ion tails exhibit a phasing that is not merely different, but fundamentally disconnected, as if one is a shadow of the other, reacting to a different conductor, a different tempo entirely? This leads us to a more speculative hypothesis, a second level of inquiry that moves beyond the comet as a simple icy dirt ball. The observed activity could be anomalously strong, or it could present spectral lines that do not correspond to any known molecular transitions in our databases. Such an event would immediately trigger an escalation in observational campaigns, a global effort to monitor the object across every available wavelength. The rational approach would be to search for more complex organic molecules or unusual mineralogical compositions in the dust that might account for the strange emissions. Perhaps the comet possesses a particularly rich inventory of prebiotic compounds, making it a unique repository of the building blocks of life, a frozen testament to the chemical generosity of the interstellar medium. The opportunity here is profound, to understand interstellar chemistry not as a theoretical construct, but as a vibrant, dynamic process made manifest in the fiery crucible of perihelion. Yet, the risk is one of profound misinterpretation, for the processes of plasma physics around an active nucleus are notoriously complex and difficult to model with perfect accuracy. Could our increasingly sophisticated models simply be failing to capture the full chaotic beauty of a natural phenomenon? Or are we glimpsing the edges of a process that is not natural at all? If the comet's outburst lacks the clear spectroscopic signature of volatile evaporation, if we see the formation of a tail and coma without the expected underlying chemistry of sublimating ices, then the very mechanism of its activity is called into question, nudging us toward a third and far more consequential level of speculation. The boldest and most unsettling hypothesis arises from the absence of an expected signal. If the perihelion passage is marked by a dramatic formation of a dust and ion tail, yet the spectral evidence for the volatile ices that should fuel such a display is absent or perplexingly muted, we are left with a profound anomaly. A comet cannot, by our current understanding, create a coma from nothing. The energy must come from somewhere. The material must be expelled by some process. The mainstream explanation would be forced to consider extreme alternatives. Perhaps the nucleus is covered in a layer of extremely dark, non-volatile material that has insulated the ices within until now. Or maybe the activity is driven by the crystallization of amorphous ice, a process that releases gas and dust from the interior. But these are ad hoc salvos for a failing paradigm. The speculative hypothesis, the one that whispers of a different kind of cosmos, is that the activity is not driven by sublimation, but by something else entirely. Could the observed thermal response be consistent, not with the slow boiling of ancient ices, but with the deliberate, managed dissipation of heat across an artificial surface? The notion of an artificial coating, a kind of smart skin designed to regulate temperature, or even to produce a specific spectroscopic signature upon command, moves from the realm of fiction into a tentative, terrifying possibility when faced with a body that behaves without a visible means of propulsion. The bifurcated tail, with its dust and ion components operating out of phase, could then be reinterpreted not as a product of separate physical forces, but as the output of two distinct systems, one for particulate matter and one for plasma, perhaps for navigation, perhaps for communication, or for a purpose we cannot yet fathom. Is the comet's breath, then, not a sigh of celestial ice, but the controlled venting of a system we were never meant to comprehend? This line of reasoning inevitably pulls our gaze from the object itself to the space it traverses, and to our own place within that expanse. The point of closest approach to Earth, a distance of approximately 1.8 astronomical units, is a number that resonates with a particular, practical urgency in the halls of our planetary defense agencies. It is a distance that is, by any sober astronomical measure, perfectly safe, a wide berth that poses no threat of collision to our world. In the algorithms that calculate impact risk, this distance would be more than sufficient to lower the object's threat classification, to relegate it from a subject of heightened interest to a mere data point in the catalogue of near-Earth objects. The criteria are based on the immutable laws of orbital mechanics, on the predictable gravitational interactions that have governed the solar system since its formation. A miss is a miss, and 1.8 astronomical units is a very wide miss indeed. But what if the criteria for a threat are too narrowly defined? We have always equated danger with the kinetic energy of an impact, with the brute force of a mountain moving at cosmic velocities. Our algorithms are designed to watch for that specific kind of catastrophe, to sound the alarm for a rock on a collision course. They are not designed to consider a different kind of proximity, a different kind of risk. What if the true significance of a close pass is not the remote possibility of a physical impact, but the simple fact of its presence, its nearness, as an active and potentially intelligent artifact? The protocols for a natural comet, even a highly active one, are well established. But what are the protocols for something that, while posing no risk of collision, challenges our very understanding of the universe? When an object demonstrates behaviors that hint at a non-natural origin, does its safe passage at 1.8 astronomical units truly constitute a lowering of the threat level? Or does it, in fact, represent the moment the threshold of an entirely different kind of alert is crossed? The void, it seems, may hold perils more subtle than mere collision, and our definitions of risk may be on the verge of a profound and necessary evolution. In the silent and perpetual ballet of the cosmos, where celestial bodies are governed by the immutable laws of gravity, a distance of 1.8 astronomical units from our world is, by all conventional measures, a comfortable margin of safety. It is a gulf so vast that it swallows the light of the sun for nearly 16 minutes, a void where the Earth is but a faint, blue speck of no immediate consequence. Yet, within the hushed, data-driven halls of planetary defense, this very same distance represents a threshold of profound and unsettling intimacy. It is the boundary where an object transitions from being a mere statistical entry in a star catalogue to a subject of intense, strategic scrutiny, a line in the sand drawn not by geology, but by the perceived potential for impact. The algorithms that safeguard our world, such as those running within the Jet Propulsion Laboratory's Scout system, are programmed to downgrade an object's threat level when its minimum orbit intersection distance is calculated to be this value, a figure that signifies a near certainty of a physical miss. But does the absence of a kinetic collision truly equate to an absence of all consequence, or are we merely privileging one form of interaction over another, potentially more subtle, yet equally significant one? The mainstream scientific explanation offers a framework of rational calm. According to current models of orbital dynamics, an object passing at 1.8 astronomical units poses a negligible gravitational perturbation to our planet or its artificial satellites. The complex equations that describe its trajectory, refined by decades of observation from facilities like the Pan-STARRS Observatory in Hawaii, allow for predictions with a high degree of confidence over centuries. Scientists suggest this could be due to the precise orbital geometry that places the object well outside our planet's gravitational keyhole, a region of space where a slight nudge could set it on a future collision course. The international early warning systems, therefore, dutifully update their risk assessment tables, shifting such an object's entry from a highlighted alert to the subdued background hum of routine surveillance. It is a testament to our growing mastery of celestial mechanics, a quiet victory of prediction over peril. But what if our definition of impact is myopically constrained to the transfer of raw kinetic energy, ignoring other, more enigmatic forms of exchange that could occur across this void? This leads us to a more speculative hypothesis, one that challenges the comforting finality of a zero-impact probability. Suppose the condition of collision equals zero holds true, but the condition of informational interference does not. The space between worlds is not empty. It is a medium saturated with the faint whispers of our civilization, radio and television broadcasts leaking into space, the precise pings of deep space network radar, the complex web of satellite communications. An object passing at this distance enters a sphere of intense human information flux. It becomes, whether by design or simple circumstance, an intermediary in this silent conversation. Could its presence, its mere physicality, subtly modulate these signals? Could it reflect, absorb, or otherwise interact with this data-rich environment in a way that we might detect, or worse, in a way that might be intended for detection by another? The very act of our observation changes the observed, but what if the observed is also, in its own passive way, observing us? The practical manifestation of this scrutiny is the opening of a strategic window of opportunity. At a distance of 1.8 astronomical units, the combined resolution of our most powerful optical telescopes and planetary radar systems, such as the formidable apparatus at the Goldstone Deep Space Communications Complex, become sufficient to construct what intelligence analysts might term a strategic portrait. The object is no longer just a point of light whose path we track. It becomes a subject for characterization. The Doppler effect, applied to radar return signals, can reveal its rotation rate. The intensity and polarization of the reflected waves can begin to hint at its surface composition and roughness. This is the second level of engagement. The maintenance of standard collision surveillance is quietly supplemented by the opening of a dossier marked Object of Strategic Interest. We are not just ensuring it will not hit us, we are beginning to ask what it is and what it might be doing here. But what secrets can a reflected signal truly hold, and are we equipped to decipher them should they deviate from the expected patterns of a simple, inert rock? The third and most profound level is triggered not by the object's trajectory, but by its character. Should the data returning from this strategic portrait reveal anomalies, a rotation rate that is non-principal axis, a radar albedo that is impossibly high or low, or a spectroscopic signature that defies classification, the object is recategorized. It becomes a special object, a designation that elevates it from a subject of interest to one of intense, focused study. The hypothesis here escalates accordingly. The reflected signal, a mere echo of our own technological prowess, could reveal far more than just mineral content. Certain materials, or certain geometric structures, could interact with electromagnetic radiation in profoundly unnatural ways. A monolithic slab of purified silicon would reflect radar differently than a porous, carbonaceous chondrite. An object with a highly ordered, crystalline internal structure could scatter light in a manner that produces a unique and telling spectroscopic fingerprint. The very fact of its anomalous reflection becomes a signal in itself, a declaration of otherness. So, when our instruments are trained upon such a visitor, are we merely studying a natural phenomenon, or are we, in fact, engaging in the first tentative steps of a forensic analysis? The opportunity presented by these close passages is the chance to refine our criteria for alert states with ever greater transparency and precision, to hone our planetary immune system to distinguish between harmless dust motes and something that requires a more nuanced response. It is a grand exercise in cosmic risk assessment. Yet, the inherent risk is one of psychological acclimatization, the phenomenon known as alert fatigue. When the public sees a headline announcing a close approach by an object that scientists have already downgraded, the nuanced understanding of orbital mechanics is lost, replaced by either undue alarm or, worse, a cynical dismissal of all such warnings. If every passage at 1.8 astronomical units is met with a sensationalized media cycle, only to be calmly explained away by experts, does the public's trust in our guardianship of the sky begin to erode? And in that erosion of trust, might we be creating a vulnerability far greater than any posed by a lump of rock and ice, a vulnerability of attention and belief? For now, the protocols are clear, the algorithms are vigilant, and the distance of 1.8 astronomical units remains a key parameter in our celestial early warning system. It is a boundary that separates the routine from the remarkable, the known from the potentially knowable. But as we lower the collision alert and maintain our watch, a deeper question lingers, one that pulls our gaze from the safety of our models and out towards the enigmatic visitor itself. What if the most significant outcome of such a close passage is not the data we gather about its trajectory, but the data we gather about its nature? What if, when we finally manage to estimate its size and composition, we find that it behaves in a way that defies our most fundamental expectations? After all, how would we react if a seemingly inert object, hanging in the void at a safe distance, began to exhibit signs of activity? What if, like the mysterious 3-eye atlas, It was found to be breathing outgassing with a vigor that far exceeds all predictions for a simple asteroid, suggesting a vitality we are only beginning to comprehend. When the Hubble Space Telescope speaks of an object breathing, the astronomical community has no choice but to listen with a profound and attentive silence, for its voice is one of unparalleled clarity in the cosmic dark. The target of its gaze, the interstellar visitor designated 3I Atlas, was already an object of intense scrutiny, a wanderer from the depths between stars, yet it was Hubble's unique resolution that revealed a most peculiar rhythm to its existence. The comet was not merely outgassing in the predictable manner of a sun-warmed icy body. It was exhibiting pulses of activity, a forceful and rhythmic expulsion of dust and gas that far exceeded all projections based on its size and solar proximity. This was not a slow, steady sigh into the vacuum, but a series of deep, powerful exhalations, as if the core of the object itself was subject to some internal, cyclical pressure. The very term breathing, though anthropomorphic, captures the unsettling regularity of the phenomenon, a cadence of light and dust that transformed this silent traveller from a simple relic of formation into an active, dynamic enigma. What internal machinery, then, could possibly drive such a vigorous and periodic discharge from so small and isolated a world? According to current models of cometary physics, such activity is driven by the sublimation of volatile ices, primarily water, but also carbon monoxide and carbon dioxide, as solar radiation heats the surface. The resulting gas carries dust aloft, creating the coma and the tails we observe. For an interstellar object, subjected to the deep freeze of interstellar space for millions, perhaps billions, of years, one might expect a crust of refractory material to have sealed away most of its volatiles, leading to a more subdued display. Yet, the data from Hubble's precise photometry and high-resolution imaging told a different story. The parameter known as AFRO, a measure of dust production within the coma, was not merely high, it was fluctuating with a significant and rapid amplitude, indicating bursts of dust ejection that could not be explained by simple, uniform surface sublimation under a constant solar wind. The mainstream explanation posits a highly heterogeneous nucleus, perhaps one riddled with fissures and vents that become active as different regions rotate into sunlight, creating a natural, if complex, pattern of jet activity. But does a simple patchwork of ice and dust truly account for the coordinated, repetitive nature of these powerful expulsions, which seem to possess a coherence that transcends the chaotic tumble of a small body? This leads us to the first, and most conservative, of the escalating hypotheses, that the nucleus of 3I Atlas possesses a naturally formed vent, a nozzle-like structure that channels sublimating gases into a focused jet. Much like a geyser on Earth, pressure could build beneath a seal of more durable material until it catastrophically fails, releasing a directed plume of vapor and dust with immense force. The rotation of the nucleus would then sweep this jet across our line of sight, creating the observed modulation in brightness. This is a level 1 hypothesis, a straightforward update to existing thermal and structural models, requiring only that we concede this visitor has a particularly fortuitous and effective geological feature. It is an elegant naturalistic solution, one that demands no new physics. Yet, the measured force of these breaths and the efficiency of the dust acceleration challenge even this enhanced model, for the energy required seems to push at the very limits of what simple solar heating can provide from an object of its modest dimensions. Could a random formation process in a distant stellar nursery consistently produce such a perfectly oriented and powerful escape valve? When the natural vent model begins to strain under the weight of the data, we are compelled to consider a more speculative, level 2 hypothesis. Perhaps what we are witnessing is not merely a geyser, but a form of thermodynamic regulation. Imagine a layer of complex, porous organic material, a mantle not unlike a sponge covering vast tracts of the nucleus. This material would act as a thermal sponge, absorbing solar radiation with high efficiency, but releasing the stored heat in a delayed, controlled manner to the volatile ices beneath. This process would create a cyclical pulse of sublimation, a slow inhalation of energy followed by a forceful exhalation of gas, a rhythm that could appear almost respiratory. The asymmetric light curve, which does not match the object's rotational period in a simple way, could be explained by this lag between insolation and outgassing, a hysteresis effect intrinsic to the material properties of the mantle itself. This introduces a fascinating new variable into cometry science, the possibility of a surface chemistry that actively modulates a comet's activity, turning it from a passive ice ball into a rhythmic, pulsating entity. But is a natural lung of complex organics a likely product of cosmic chemistry, or does its apparent efficiency border on the engineered? The most profound, and therefore most cautiously approached, hypothesis resides at level 3. It dares to posit that the modulation is not a product of natural geology or complex chemistry, but of something far more deliberate, a form of shielding or a technology for regulating the internal environment. One could envision an artificial baffle, a variable aperture designed to control the flux of solar radiation, reaching a sensitive core, perhaps to maintain a stable internal temperature against the varying intensity of stellar light during an epic journey. The rhythmic breathing would then be a byproduct of this system's operation, a periodic venting to release excess pressure or a cycling of a protective cover. The cadence noted in the data would not be a mere statistical artifact, but the signature of a control system, a purposeful rhythm utterly distinct from the stochastic chaos of natural phenomena. This hypothesis does not leap to the conclusion of consciousness, but it does force a rigorous investigation into technological plausibility, a field known as the search for technosignatures. It transforms the observation from a purely astrophysical puzzle into a potential moment of contact, however passive and enigmatic. Are we therefore looking at the weathered and dormant hull of a vessel, its automated systems still faintly pulsing as it journeys on, utterly indifferent to the watchers in this remote star system? The evidence that fuels this tripartite inquiry is as precise as it is provocative. Hubble's spatial resolution allowed astronomers to separate the nucleus's faint glow from the surrounding halo of dust, providing a clean measurement of the afroparameter. Its anomalous increase was the first clue, the initial quickening of the pulse that signaled something was amiss. The phased light curve, which charts brightness against rotational phase, further revealed the story. The brightening events were not symmetrical. They were sharp, steep rises followed by more gradual declines, a profile characteristic of a directed jet swinging into view rather than a broad, sunlit surface rotating into sight. And when compared to the only other known interstellar comet, 2I Borisov, the difference was stark. 2I Borisov behaved largely as expected, a sublimating iceberg on a graceful arc. 3I Atlas, however, displayed a variability of much greater amplitude, a hyperactivity that screams of focused, directional forces at work. The jets, if that is what they are, seem too well defined, too potent. Do the quiet, predictable whispers of 2I Borisov serve to highlight the frantic, structured language of 3I Atlas, or are we simply witnessing the vast spectrum of natural diversity between two interstellar orphans? This entire intellectual exercise presents a fundamental duality, a tension between a profound opportunity and a subtle risk. The opportunity is magnificent. To understand the mechanics of outgassing in an object forged around another star, to potentially discover new physics of heat transfer and material science in the extreme environment of a small body. Every anomalous data point from 3I Atlas is a window into the universal processes of planetary system formation, a chance to see if the rules we have deduced from our own solar system hold true in the galactic expanse. The risk, however, is the perennial siren song of the unknown, the the temptation to anthropomorphize and technologize every anomaly we cannot immediately explain. To immediately attribute the rhythmic breathing of Three-Eye Atlas to an artificial regulator is to risk what historians of science call the consciousness of the gaps fallacy, where any unexplained phenomenon becomes evidence for intelligence. In doing so, we might blind ourselves to a truly novel, but entirely natural, physical process, a new type of cometary behavior waiting to be understood. Are we, in our desire for cosmic company, potentially misinterpreting the first pages of a new chapter in astrophysics as a message, and in doing so, failing to learn the new language in which it is written? As Hubble's deep gaze documented the intricate dance of dust and light from the nucleus itself, another formidable set of eyes was turning towards the visitor's extended form, studying the consequences of its vigorous life. For the tale of a comet is written not only in the brilliance of its core, but in the vast, spreading plume of its aftermath, a ghostly trail that may hold the ultimate clues to its origin and nature. What story, then, would be told by the growing tale of Three-Eye Atlas, as seen by the powerful ground-based observatories of the NOIRL consortium, and how would its dusty signature compare to the familiar comets of our own celestial backyard? It begins not with fire or ice, but with light, a silent autobiography written in scattered photons. When a comet ventures into the inner sanctum of a star, the solar wind and radiation pressure perform a delicate act of excavation, sweeping away the primordial dust and ice to sculpt a tale that streams across the void. This luminous trail is a historical document, its very structure and composition a record of the body's origin and the conditions of its long journey through the dark. Our own solar system possesses a vast library of such autobiographies, each comet's tale, be it dust or ion, telling a familiar story of water ice, carbon dioxide, and silicate grains, all bound by the common heritage of our protoplanetary disk. We have learned to read these scripts, to predict their behavior, to understand the grammar of their growth and dissipation under the sun's relentless influence. But what happens when the author is not from this library? When the pages of this autobiography were written in a stellar system far beyond our own? The recent observations from the NOR lab facility, utilizing the powerful dark energy camera, have captured the growth profile of a dust tail belonging to an interstellar visitor, a profile that deviates from every known text in our collection, suggesting a narrative composed under a different set of physical laws, or perhaps for a different purpose entirely. Could it be that we are not merely reading a natural history, but a deliberately crafted message, or the artifact of a technology that manipulates the very fabric of space dust? According to current models of astrophysics, the formation of a cometary dust tail is a straightforward, if complex, process. Sunlight exerts a gentle but constant radiation pressure on microscopic particles liberated from the nucleus by sublimating ices, pushing them away from the sun and into the characteristic curved sweep of the dust tail. The rate of this tail's growth, its density, and its morphology are dictated by the size distribution of the dust grains, their composition, and the strength of the solar wind. When we compare the NOILAB data of this interstellar object to our extensive library of native comets, the first and most immediate anomaly is the growth law of the tail itself. It does not expand and diffuse as predicted. Instead, it accrues mass and length at a rate that suggests a population of dust grains with fundamentally different mechanical properties, grains that are perhaps older, more sintered, and more resilient than anything formed within the turbulent cradle of our own solar system. The conventional explanation would point to a unique formation history in an alien protoplanetary disk, one subjected to different temperatures, densities, and cosmic ray fluxes, which could indeed create dust with a unique cohesion and size distribution. But does a simple variation in natal environment fully account for the precise and structured manner in which this tale is unfolding, as if each particle knows its place in a grander architecture. This leads us to the first and most conservative of our escalating hypotheses, that the difference is merely one of history. The interstellar medium is a harsh bath of cosmic radiation, and a wanderer travelling for millions or billions of years between stars would have its constituent materials thoroughly processed by this relentless exposure. The dust grains within it would not be the relatively fresh, pristine particles shed by a young comet from the Oort cloud, but ancient, irradiated, and potentially cross-linked grains, their surfaces annealed and their internal structure altered. Such old dust would respond differently to the forces of radiation pressure and solar wind, potentially accounting for the anomalous growth profile observed by the DCAM's meticulous time series data. The tail thickens not because of a greater quantity of dust, but because each grain is more robust, less prone to fragmentation, and thus maintains its integrity within the tail's structure for a longer period. It is a simple, elegant, and perfectly plausible explanation, rooted in established material science. Yet, if the dust is merely old and hardy, why does the polarimetric data, which measures the polarization of sunlight scattered by the tail, reveal not just an anomaly in size, but a startling and consistent asymmetry in the particle's electrical charge? The plot, as written in the language of polarized light, thickens. Polarimetric observations from a global network of telescopes have provided a second critical layer of data, analyzing the color and polarization curves of the scattered light to infer the size, shape, and electrical nature of the dust particles. Here, the mainstream scientific explanation encounters a more significant challenge. The data suggests that the particles within the interstellar tail carry an electrical charge signature that is both unusually high and anomalously uniform. Within our own system, cometary dust charges vary widely, creating a complex plasma environment that interacts chaotically with the solar wind. This object, however, displays a tail where the particles seem to be in a state of coordinated charge, leading to a far more structured and forceful interaction with the magnetized plasma of the solar wind. Scientists suggest this could be due to a unique mineral composition in the object's home system, one rich in materials that become triboelectrically charged through collisions, or that possess a high photoelectric yield, causing them to emit electrons more efficiently under ultraviolet light. But that does not account for the formation of a tail whose central column remains so sharply defined, so resistant to the dissipative forces that invariably blur and fan the tails of even the most active native comets. Thus, we are compelled to consider a second, more speculative hypothesis, that the tail's morphology is not a product of passive charging, but of an active plasma phenomenon. The unusually and uniformly charged particles are not merely reacting to the solar wind, they are shaping it and being shaped by it, in a feedback loop that gives rise to a coherent structure. The high charge would create intense local electric fields, causing the particles to align and self-organize, resisting the tendency to diffuse and instead forming the observed columnar, almost chimney-like, tail. This plasma sculpting could explain the crisp, sharp-boundaried profile that so confounds conventional models. It would be a natural, if rare, plasma physics effect, a testament to the complex and often counterintuitive behaviors of charged matter in space. But if this is a natural self-organization of plasma, why does the geometry of this chimney exhibit such a startlingly regular and tubular cross-section, a morphology that is far more reminiscent of engineered structures than of any known fluid, dynamic, or plasma instability? The most profound mystery is etched into the very silhouette of the tail, a feature the data reduction pipelines initially flagged as a potential instrumental artifact, a sharp, linear discontinuity running along the tail's axis, like the seam of a pipe or the shadow of a supporting truss. In our solar system, cometary tails are diffuse, fuzzy, and graded in their density. They are clouds, not constructions. The mainstream approach would be to exhaust every possible explanation involving atmospheric distortion, telescope optics, or data processing algorithms before ever entertaining a more extraordinary conclusion. Teams of astronomers and engineers would meticulously model the point spread function of the dark energy camera, analyze the atmospheric seeing conditions during the observations, and search for any pixel-level anomalies that could create such a sharp, artificial-looking feature. The null hypothesis must always be that the anomaly is ours, not the cosmos's. However, certain anomalies defy all conventional and instrumental explanations, and when every terrestrial and instrumental source of error has been accounted for and eliminated, the anomaly itself becomes the data. What if the sharp boundary is not an error, but a feature? This forces us to confront the third and most profound level of our hypothesis, that the morphology is not entirely natural. We have moved from altered history to active plasma physics, and now to the precipice of a technological interpretation. The chimney or tube structure, maintained against all dispersive forces, could be read as a form of architecture, a scaffold, or a waveguide on a scale of tens of thousands of kilometers. Perhaps the dust is not merely being shed, but is being arranged. Could the charged particles be acting as a distributed antenna, a vast transient structure for communication or energy collection? Or might we be witnessing the remnants of a form of propulsion or navigation, where a craft utilizes a manipulated dust field as a shield or a beacon? The very idea seems to belong to the realm of science fiction, yet it is a hypothesis that emerges stubbornly from the data when all lesser hypotheses prove insufficient. The risk, of course, is immense, for in our desire to find significance, we may be conflating an intricate, natural phenomenon with a technological signature, a peril that has beset the field of astronomy since the first mistaken canals of Mars. But what is the greater risk? To prematurely embrace a fantastical idea, or to prematurely dismiss a genuine one because it does not conform to our current understanding of what is possible? This interstellar visitor, with its enigmatic and structured tale, presents not merely a puzzle for astrophysics, but a tangible test case for the future of interstellar travel. The dust environment around other stars is a critical unknown for any prospective spacecraft designed to travel between them. A vessel moving at a significant fraction of the speed of light would find even a microscopic grain of interstellar dust to be a potentially catastrophic projectile. The data from this object offers a rare opportunity to test our models of interstellar dust grain properties, their distribution, and their interaction with high-velocity objects. Understanding whether this dust is merely ancient and hardy, or whether it can become organized into coherent, rigid structures, is of paramount practical importance. It dictates the design of shields, navigational sensors, and propulsion systems for any vessel daring enough to leave the protective heliosphere of our Sunday. But if the dust can be manipulated, could it also be weaponized, or could it be used to conceal a presence within a seemingly natural cometary haze? The line between a natural anomaly and a strategic one becomes perilously thin when the medium is the entirety of interstellar space. Are we studying a curious natural phenomenon, or are we, for the first time, analyzing the engineering principles of a technology that operates on a cosmic scale? The trail of scattered photons leads us from the certainties of our own solar system to the enigmatic shores of another, leaving us with more questions than answers. The autobiography of this interstellar wanderer is written in a dialect of physics we are only beginning to decipher, a narrative where dust behaves not as inert matter, but as an active component in a drama whose full scope we can scarcely imagine. We are left staring at the data, at the sharp, unnatural line within the growing tale, wondering if we are witnessing the simple, if complex, weathering of an ancient rock, or the operational signature of something that has learned to write its own story directly upon the canvas of the cosmos. And as we turn our eyes from the deep space of Neulab's discovery to the rust-coloured sands of our planetary neighbour, we are confronted with another enigmatic trace, another mark upon a world that challenges our perception. For within the vast, empty stillness of the Martian landscape, the Perseverance rover has imaged a formation of its own, a long, linear, columnar streak stretching for tens of thousands of kilometers across the surface, a mark so immense and so precise that it forces upon us a similarly disquieting choice of interpretations. Is this the straightforward result of a long exposure, capturing a star trail in the Martian sky, a simple trick of perception and camera mechanics, or does it represent a morphological anomaly of a different, perhaps geological, perhaps not, nature altogether? The Martian horizon, as perceived by the unblinking eyes of the Perseverance rover, presents a vista of profound and desolate beauty. A panorama of rust-colored dunes and jagged peaks under a tenuous, peach-hued sky. Yet, within this seemingly sterile landscape, a single, stubborn anomaly has emerged from the data stream, a slender thread of light stretching across the frame, challenging our perception of the red planet. This is not a casual streak of cosmic radiation impacting the sensor, nor the fleeting passage of a high-altitude cloud. This is a persistent, coherent column, a luminous filament etched against the darkness of space, tens of thousands of kilometers in apparent length. Its very existence forces upon us a fundamental, almost philosophical choice. Are we witnessing a simple trick of the light, a mere artifact of our own mechanical envoy's perception, or are we gazing upon the contours of a physical object, a structure whose nature and origin lie entirely outside our current lexicon of celestial phenomena? Does this pillar represent a flaw in our vision, or a feature of a reality we have only just begun to perceive? The most immediate and parsimonious explanation, the one that adheres most strictly to the principle of Occam's razor, lies not in the Martian environment itself, but within the intricate silicon and circuitry of the Mars-Cam-Z instrument. According to current models of digital imaging, particularly under the extreme low-light conditions of a Martian night, a phenomenon known as pixel blooming, or charge bleeding, can occur. In this scenario, an intensely bright point source, such as a star shining with unusual ferocity through the thin atmosphere, or even the distant glint of sunlight on a piece of orbital debris, can overwhelm a single photosite on the sensor. The excess electrical charge, like water overflowing a cup, then spills into adjacent pixels along the column of the sensor's readout architecture, creating a perfectly vertical streak of light that is entirely a creation of the camera's internal processes. This explanation is elegant in its simplicity, requiring no new physics, no unseen actors on the Martian stage. It is a known, documented artifact of our own technology, a ghost in the machine we ourselves built. The prescribed response is one of calibration and procedure, to adjust the firmware, to update the standard operating protocols for long-exposure astrophotography, and to systematically eliminate this digital phantom from our future observations. But what if the ghost is not in the machine, but in the landscape itself, a spectral presence that our instruments, by their very design, are only now becoming sensitive enough to accidentally capture? However, this conventional diagnosis begins to fray at the edges when one subjects the image to a more rigorous, pixel-level interrogation, for the anomaly displays a subtle coherence that transcends the typical behavior of sensor noise. If we move beyond the initial, superficial assessment and delve into the raw data from both the Mars-Cam-Z and the Nav-Cam systems, cross-referencing the precise orientation of this luminous column with independent datasets, a more complex picture emerges. By aligning the pillar's axis with the solar wind vector, at the exact moment of capture data meticulously recorded by missions like MAVEN, which constantly monitors the sun's energetic outflow, a compelling correlation may be found. Should the pillar's alignment prove not to be a fixed artifact of the rover's orientation, but instead track dynamically with the shifting direction of the interplanetary magnetic field, the hypothesis of a simple sensor bloom collapses. This would suggest an interaction not with the camera's sensor, but with the Martian environment itself, pointing towards a transient, macroscopic structure of ionized gas, a plasma morphology shaped by forces we are only beginning to understand. Could the tenuous Martian atmosphere, under the relentless lash of the solar wind, be capable of self-organizing into such a stark, linear formation, a temporary column of ionized particles tracing the invisible lines of magnetic force that drape themselves across the planet? And if so, what unknown processes of atmospheric electrodynamics, what peculiarities of the local magnetic field could give rise to a structure of such remarkable length and stability? Yet, the speculation need not halt at the boundaries of known plasma physics, for the human mind, once presented with an anomaly, is compelled to explore the outermost realms of possibility. The third hypothesis, the most speculative, and therefore the most potent in its implications, dares to consider the pillar not as a natural formation, nor a technological artifact, but as a reflection. The premise is audacious, that the streak of light is the result of a directed beam, a coherent signal of immense power, glancing off a perfectly flat, unnaturally smooth surface, somewhere within the rover's field of view, a mirror, for lack of a better term, placed upon the Martian soil. This would account for the pillar's sharp definition, its apparent length, and its persistence across multiple frames. The investigative pathway this unlocks is one of profound consequence, elevating the inquiry from a scientific curiosity to a matter of strategic planetary security, albeit one that must be approached with the utmost discretion and a listen-only protocol, observing without provoking, seeking to understand without announcing our presence. But if this is a reflection, a deliberate signal, from whom or from what does it originate, and what message, intended or otherwise, does its mere existence convey? Thus, a single, enigmatic image transforms the desolate plains of Jezero crater into a profound natural laboratory, a crucible where the mundane interactions of dust and electromagnetic fields collide with the most extraordinary of possibilities. The opportunity is unparalleled, to use this one photograph as a key to unlock new understandings of Martian atmospheric physics, or perhaps something far grander. The risk, however, is equally immense, for it lies in the potential for a monumental misstep, the chance that a critical decision regarding our future exploration, or even our conception of our place in the cosmos, could be based on nothing more than a photographic artifact, a trick of light and shadow on a distant, dead world. But what if the artifact is not an error, but an intentional signature, a clue left not by nature, but by intelligence? And what then would be the consequences of our failure to recognize it for what it is? The investigation, therefore, must proceed on three distinct and escalating levels, each a gateway to a deeper, more disquieting understanding. The first level remains firmly grounded in the practical, a systematic effort to debunk the anomaly through technical means, to prove it a child of our own technology. The second level accepts the pillar as a real, physical phenomenon of the Martian environment, a puzzle of plasma and magnetic fields that challenges our existing models. But it is the third level, the contemplation of a deliberate, reflective origin, that truly reconfigures the landscape of the inquiry, forcing us to look not just at the planet beneath our rover's wheels, but beyond it, to the ancient depths of space from which such a presence might have come. For if this pillar of light is a beacon, however unintentional, its source cannot be local. It must be a whisper from the void, a signal whose journey began not on Mars, but in a place of unimaginable antiquity, a place like the dim, swirling outskirts of our own galaxy, where time itself moves to a different rhythm and the seeds of cosmic history are sown. Could the key to this Martian riddle lie not in the red dust at our feet, but in the faint, swirling starlight of the galactic fringe, in the primordial nurseries from which the first stars and their potential companions emerged?